Okay, so I would like to welcome you to the COST Epigraphy Action project. This is the Colloquium Series. So we are very much pleased to launch this new series. And by having this series, actually, we have been aiming to bring together the leading experts and the researchers. Then they can share their insights and we can have inspirations and we can also have good and fruitful discussions. So about the advanced technologies and the fundamental of the science. So it's a really great pleasure for us to introduce the very first guest speaker, James Clegg. Dr. Clegg is a principal optical scientist at Microsoft Research in Cambridge in United Kingdom. So his work focuses on cutting edge developments in optical systems and their applications to next generation computing technologies. So today he will be presenting us a talk entitled as Analog Optical Computing at Microsoft Research UK, Improving Efficiency in the AI Area. So in this talk, he will explore how optical computing approaches can address the growing computational demands at AI, offering new pathways toward more efficient and scalable solutions. So please join me welcoming Dr. Clegg. So floor is yours, James, please.
Thank you very much for the introduction. So it's really nice to be here talking to you today. I was just saying before the call started that I've had a lot of interest in CERN. I got to go to CERN on a school trip in 2003 and see the CMS machine when the tunnel was still open and see Atlas and kind of being built on a big factory floor. And then I studied quite a lot of particle physics as an undergraduate physicist. So yeah, it's always been kind of like CERN and particle physics has always been a nice interest of mine. So today I'm here to talk to you about an analog optical computer for machine learning and optimization. So I work at Microsoft Research UK, which is in Cambridge in the United Kingdom, and we've been working on this project for the last few years, sort of the last 3 or 4 years. So the talk will cover what we have been doing, and mostly we'll talk about our past results. But at the end, I would like to talk a bit about what we're doing sort of right now and in future as well. So firstly, by way of motivation, so why do we need a new type of computer? Well, existing hardware, and by that I mean existing types of computers, especially GPUs, are struggling to keep up with AI workloads. And a nice headline figure is that in 2022 to 23, Microsoft consumed 24 terawatt hours of electricity. And that's about double what it was 3 years earlier. And that doubling is probably largely due to, in that year, starting to run a lot more AI workloads. And up until that year, so that number comes out of the 2024 sustainability report for Microsoft. And up until that year, Microsoft were publishing their annual electricity consumption. And since then, they no longer published the number, or at least it wasn't published in last year's report. So probably that's because the number is getting really quite large now. And 24 terawatt hours, just to put that in context. So the UK's annual electricity generation is something like 240 terawatt hours. So it's about 10% of a decent sized European economy. Over that time, Moore's law has slowed down as well. So if you look at the dollar cost per billion transistors, and as a function of the transistor node size, which is also like as a function of time, so the node size gets smaller and smaller over time. The dollar cost hasn't really been dropping for the last generations. Having said that, GPUs have been getting significantly better, but we believe that the reason that they have been getting better is largely through becoming more specialized and more tailored to the particular jobs that they're trying to do. This pie chart here is an estimate from Bill Daly from NVIDIA, his estimate is that 92% of the performance gains coming from GPUs come from them becoming more specialized, and only sort of 7 or 8%, the remainder, come from the transistors themselves actually getting smaller. And specialization in the context of a GPU means that they are sort of designing the GPU to do, more particularly designing it to do the job it's really trying to do. So matching the size of tensor cores to the expected size of operations, for example, or using lower bit precision representations, because many AI things don't need sort of 32-bit or 64-bit numbers like you would do in sort of traditional physics simulation, say. And also they implement complex instructions directly at the lowest level in the hardware. So, for example, attention mechanisms, which is an important part of how LLMs work, are implemented quite close to the bare hardware, and at the same time also exploiting sparsity. So lots of the matrix multiplications that are done are sparse matrix multiplications, and you can design the chip to make use of that. So those two things together mean we believe we need a new type of computer, and we think it's a perfect time for analog computing to tackle that challenge. And we think, in particular, analog is good because many analog computers in the past have been sort of tailored, and they've been perfect for specialized applications, rather than sort of a general CPU type computer that can do anything. You can build an analog computer that can do a particular job very well, and that's what our computer is like. So before I talk about the design, I'll just summarize sort of where we are today on the project and with our work. So we have working hardware in the lab that can run a number of different applications. And the two I'll talk about today are a machine learning application. So we can do classification, and we have a demonstration that I'll show you, where we can classify handwritten digits from, this is trained on the MNIST data set. And there the machine, actually, so for all of these results, the machine is 2,300 weights in size, and I'll come on to say what that means. But because it's doing vector by matrix multiplication, what I mean there is that there are about 2,300 weights in the matrix, so it's a size of about roughly 50 by 50. So the vector is of length 50. We are also now, with some recent results, able to run diffusion models on the hardware. So MNIST classification is in machine learning circles considered a bit easy or old-fashioned, and diffusion is a more kind of modern, more exciting machine learning application. And we have a paper in submission that's under review at the moment on that work. In addition, we also looked at, sort of separate from machine learning, looked at solving optimization problems. So we had a collaboration with Barclays that ran for a few years, and also we worked on some medical MRI image reconstruction. And together, so the MNIST classification and the MRI and the financial optimization problems, all those results were published last year in a Nature paper, which you can find online, open access. Okay, so now I'm going to move on and we've done the recap, the intro, and I'm going to talk about the design of the machine and how we work. Because the machine is extremely specialized, and because many analog computers are, it's really important to develop the hardware and the applications together. And first I'm going to talk about the hardware and how it works, and then we'll come on to the applications and the results. But it's important to know, sort of in the way the project's been working up until now, that we weren't just kind of building something in the lab, building some optics thing and throwing it over to computer scientists or mathematicians and say, go and work out what you can do with this. There's a sort of two-way feedback process with them sort of saying what things might be useful and so on. Let's look at the hardware and the design first. And it's really, so I've been mentioning it as an analog computer. It's really a combination of optics and electronics that are working together to make our computations work. And I'd like to take a minute to explain how. So it's a specialized computer, and it's specialized because it's an iterative solver, and it finds fixed points of systems of differential equations. And it does that by signals propagating around in a loop iteratively. So let's just start somewhere in the loop here. And the colored part with all the colored lines are a representation of vector by matrix multiplication in the optical domain. So the different colors there don't represent wavelengths, they represent different vector values. So in this diagram, this would be a 4-element vector and a 4x4 matrix, and we would say this system had 16 weights. So here, let's just say you're at the point where the colored dot. In fact, I'm going to use the laser pointer. Hopefully, you can see that. So if you're over here, this is the input vector. And I know that this is a loop, but we're just going to start somewhere in the loop. So we're going to start at the input vector. These light sources are then spread out using optics. Obviously, the optical elements are not drawn here, onto a 4x4 matrix, which is a matrix of basically programmable absorptive filters. And so the input light, the input vector, gets multiplied element-wise by the matrix, and then we sum down to some photodiodes here. For many applications, it's really important to have nonlinearity in the loop. So we decided to implement the nonlinearity electronically. You could implement nonlinearity optically, but many optical nonlinearities require sort of very specialized systems like extremely high power or like very exotic materials or both. And that's not really compatible with our aim to be energy efficient. So in this case here, you'd have 4 output elements which are going round then through the nonlinearity electronically, and then they get converted back to driving signals for light sources, and then signals propagate around this loop. And the signals propagate around in our system unclocked and sort of at the speed of light effectively. So zooming in on what the optics is doing for us here. So the optics is doing the linear operations, as I said. And the first thing we need to do is to take each vector element and spread it out into a row on a matrix. We call that the fan-out system or the spreading system. We then need the multiplying system, and for that we've got basically a spatial light modulator, which is a computer-controlled set of absorptive filters, and you get a voltage per pixel. You can control the voltage on that pixel, and you get to choose how much light propagates through. So if I click there, we've got a little animation. And then you have the summing optics, which is or the collector or the fan-in optics, which collecting drawn like this, they're collecting columns of light and summing them onto photodiodes, and where they are summed up effectively. So mathematically, just representing it all mathematically, we've got our input vector of light sources, which is our x. The weights matrix in machine learning language is then a matrix of programmable gray filters and their amplitude modulators. I didn't say that this is all done incoherently, so there's no coherence here, or it's all done with modulating the intensity of the light, not the phase, and detecting the intensity, not the phase. And then we have y, our output vector, and also because this weights matrix is a set of it is programmable. That means you can run different models or solve different optimization problems or whatever it might be by just programming a different problem into that modulator. This system obviously gives us the ability to have massive parallelization. So we get 1 million operations for the scale that we're aiming for our system is 1000 by 1000 matrix size, which gives you 1 million weights sort of passively and for free in a single pass of the light. And kind of inherent in the diagrams I've been showing you is that this is a three-dimensional optical architecture, and many of the state of the art and our competitors who are doing optical computing or analog electronic computing are doing everything in the plane, so in the plane of the chip. And the problem is there that you end up with using a lot of chip area for routing. So I'm just taking this picture here. So if you imagine you have an input vector of input vector x, a weights matrix w with n squared elements, and an output vector y, then if you just draw the wires that you would need to connect one of the x's to one of the y's, you can see this is going to look extremely complicated when even if I drew all the wires required for this 4x4 system, and really horrifically complicated for a 1,000 by 1,000 system. So there's kind of order n squared chip area required for the fan in and fan out wires or light pipes, whatever it might be, depending on your application. And that doesn't scale very well. In comparison, we're using a 3D optical architecture. And what we mean by that is that the light is propagating out of the plane in free space, using sort of waveguides or small lenses to couple the planes together. So we've got sort of three different planes, X, W, and Y, and lenses or waveguides in between. So the routing problem is much simpler here, and that leads to the system being much more scalable. So you've seen a lot of diagrams so far, but here's a picture of what the system actually looks like in the lab. Here we're looking at something that's about 35 or 40 by 40 centimeters in area and about 20 centimeters tall. And the lenses you can see there are sort of 50 millimeter diameter, roughly. So everything's reasonably bulky at the moment, and we'll come on to that later in the talk and how we're going to address that. But at this stage, let's just kind of go through the oops, just gone ahead too far there. Let's go through the diagram. So zooming in on the sort of interesting bit in the middle. So you can see that blue glow there. Those are some that's some light coming from an array of micro LEDs. So our optical sources in this setup are micro LEDs. The chip that controls these micro LEDs is about the size of an A4 piece of paper, and that's what you can see there in green. And the LEDs themselves are that little tiny bit in the middle under the laser pointer, and all of the rest of the stuff is discrete PCB level amplifiers and drivers. And that's something which would need to be, again, shrunk down and when we scale up. The light from those LEDs is captured by a series of lenses and is directed towards the spatial light modulators where the weights are. And we're using a mixture of cylindrical and spherical optics. I'll come on to that in a minute for anyone who's interested in optics. The projector itself is a spatial light modulator, which has about 2,000 by 2,000 pixels. And then the detection optics is over the collection and summing is done on the CMOS sensor over here. And again, it's a similar kind of arrangement to the micro LED board here. So it's about an A4 sized thing with some little active area in the center under the laser pointer, which is millimeter sized. And then around it, we've got this large collection of amplifiers. The optical system looks like this, and the reason I'm showing this is because I wanted to say how we're using a combination of spherical and cylindrical optics. So the operation of the spreading and the merging, the spreading and the fan out and the fan in is kind of asymmetric by nature. And so the traditional approach to doing this will be to use entirely cylindrical lenses and to use like interleaved 4F and 2F systems. But that doesn't work very well because firstly, it's hard to prototype with those systems. The cylindrical optics you buy are all plano convex and therefore low quality. It's hard to get good resolution. And even at production, your cylindrical optics are harder to polish and therefore more expensive than spherical optics. So what we've gone for here is a kind of hybrid approach where we're trying to do most of the imaging with spherical optics and then just add a little bit of cylindrical power to do the spreading and merging operation. And the other thing that this diagram shows you, which was harder to see before, is that we're able to do signed mathematical operations because so our sources are unpolarized and we're splitting the light with polarizing beam splitters into two polarizations. That gives us a lossless way of getting two separate light paths. And then we can do two intensity calculations there. Oh, the light's just gone off. Excuse me. We can do two intensity calculations there to give us like two separate electrical signals, which can then be differenced electronically to give us a signed operation. Some details about the spatial light modulator for anyone who's interested. It's an SMD displays device. Oh, I said 2,000 by 2,000 pixels. It's smaller than that, so 1,920 by 1080. And the pixels are sort of 8.5 micron sized. The nonlinear operations are done electronically with a combination of BJTs. And the important thing about this really is just that this is controllable, so we can control the amount of nonlinearity. This is another thing that would be hard to do optically. So we've combined these transistors together to give us a hyperbolic tangent response, which is like as shown in this green line here. And we can adjust both the gradient of this line, this function, so the gradient around the origin, and also the saturation point. And so we can quite accurately control the nonlinear response. And so, for example, if you have not very much saturation and a low gradient, this is just like a linear response. And for some applications, that's good. Or you might want to have a very steep gradient and a strong saturation, and that's much more like a step function response. Okay, so that was the section about the hardware and how it works. And now I want to start talking about some results. We'll start with the optimization, where this is an example of working together with the mathematicians on the team. So the standard way that competitors do optimization problems in hardware, for example, in quantum hardware, is to use an abstraction called QUBO, which means quadratic binary optimization. And in that approach, every single variable in the system is a binary variable. And that's not a very natural way to express many optimization problems, where for real world values, you want a mixture of continuous and binary. So some mathematicians on our team have come up with a new optimization framework called quadratic mixed optimization, QMO, and that allows us to express a mixture of some continuous and some binary variables. And that maps very well to our hardware with our controllable nonlinearity, because the binary variables can be set with a high gain and a strong saturation, and the continuous ones more with a linear response. As an example, we had a collaboration with Barclays, and we were able to solve a financial transaction settlement problem for them. And this is a problem where you imagine a series of banks all trying to send some money to each other in a kind of network graph structure, and you want to find the best, smallest set of transactions that can be made to make sure all the right money ends up in the right places. And then we also worked on MRI imaging. So here, many of you will probably know that that in a standard MRI machine, you can make it go faster by undersampling the input and using something called compressive sensing to reconstruct a sort of faithful representation of what you would have seen if you'd fully sampled the input. And this system so your input data is undersampled, and you need then an optimization algorithm to find the most likely real image that goes with your measurement. And the idea here is, well, we can use QMO as that optimizer and our machine as that optimization step. And if you can make a better optimizer, you can then reduce the amount of sampling required, so you can do even more undersampling, and that translates directly into less patient time in a machine, for example. For machine learning, I'll talk about this a bit more in detail, but and how it works in the next slide. But the key results are we've been able to do classification. I mentioned this already, so you can write a handwritten digit, and the system will tell you what digit it thinks it is. Run a regression problem, and also now run some diffusion as well. So I talked about our machine being a fixed point solver, and that might surprise you that we're able to run machine learning inference on this machine, given that machine learning models conventionally don't really look like fixed point systems. And I'll just sort of take a minute to explain what's going on here. So with a conventional machine learning model, you have an input, and it passes through a stack of a series of weights matrix multiplications and element-wise nonlinearities. But as you go through this stack, the weights and the nonlinearities are different at every stage in the multi-layer process. And this is another example of working together with the algorithm teams or machine learning teams, where here they were able to work on a different class of machine learning models called deep equilibrium models. And deep equilibrium models are a stack of layers, so a stack of matrix multiplications and nonlinearities, but you put that whole stack in a feedback loop, and you iterate through that system until you get convergence. And in our system, in our experiments, there's actually a small number of layers here, but it's the same concept as shown on this diagram. So the results from the classification. Oh, and this is also just to say a bit about how the training works. So to train a system, a machine learning system, you need to get access to the gradients and the values of all of the intermediate variables. And that's something that's very difficult with the hardware. So what we did was built a very detailed copy of the hardware including all its imperfections in simulation. And so sort of very, very carefully measuring everything, measuring all the noise levels and all the imperfections and putting that into a model. And then we trained the network weights on the copy, on the digital twin, and then we run inference on the actual machine. So example of some regression results there. There are two different curves there. So again, here what we're doing is we would send an input X into the system and we want it to predict the Y value given X. And there are some results here showing the green bars are showing the results from the machine. So you can see there's some spread there, but it's doing a good job of predicting both the Gaussian and the polynomial shape. And the classification results, I'll come on to showing a demo for that in a minute, but there are kind of two important points here. We got, very good degree of accuracy, so 95% classification accuracy. And more importantly, or equally importantly, which validates our approach to train on the digital twin is that there's a really extremely high degree of accuracy, a match between the digital twin and the hardware results. For diffusion models, so people might know that diffusion models themselves are iterative, but it doesn't work to just directly use diffusion models out of the box on our system. And our team has come up with a stepwise diffusion process where we break down each diffusion step into a fixed point search. So what actually happens here is you can see the start of the process. You start off, we're trying to here generate the letter A. We start off at time t equals 0 and run a fixed point search, which kind of gets us sort of slightly closer to the A. And then we pass that back and go to the next diffusion step and run fixed point search on the hardware again and keep going until eventually we get to our letter A. And the point here really about doing this, not just all in one fixed point search, is that we don't want to run the diffusion process all the way until convergence, because convergence means finding a global minimum. And for a diffusion model, that means modal collapse. So there's no diversity in your outputs, which is bad because you want to generate many different potential images given an input. So we had actually a 4-layer model, and you can see here we've got some simulation results in green and some actual hardware results in purple. Just to say here, we're not diffusing and making the whole image of these letters. We are doing it point by point because of the small scale of the system. So in fact, here we're generating pairs of coordinates effectively, and then plotting all the coordinates and showing that they cluster in the right shapes. But with a latent space model, where there's sort of an input and an output layer as well, we are able to do full image diffusion of full images. And for example, here in what's labeled panel B, there are some letters, MNIST, these have been generated now by the hardware, or some samples from the fashion MNIST data set. Now I'm going to try and show our live demo of the digit classification, and this will mean I need to stop sharing my screen and start showing a different window. So just bear with me and hopefully this works. I'm going to just stop sharing. I need to reshare. Let's try this. Share. So yeah, please can someone just unmute and tell me if you can see?
Yes, we can see.
A screen.
Yes, we can see.
Okay, great. So this is now our kind of web front end, and if I do handwriting on this screen, it'll get sent to our machine, which is running in the lab. Unfortunately, I can't show you that it's actually running in the lab. We haven't got a webcam going, but it really is working. So I can write a number on here and press submit. You can see it worked for 3, and it won't work all the time, but hopefully we get lucky here. Okay, so here we go. It's actually got this one wrong, and it says it's more likely to be an 8. I actually can't see the screen because I've got the Zoom window over. Okay, so that was a bad example, but we can try a few more examples, and hopefully we'll get some success. But anyway, maybe it's good to see that it doesn't work all the time because it shows you that it's it's real. So, for example, here, and you can also try sending in other stuff that doesn't even look like a I don't know what that's going to do. Send in a weird shape, and it may sometimes it kind of does what you would hope it would do, and sort of predict noise, and sometimes it confidently says it's wrong. But in this case, I guess maybe that could be a 0. And let's have one more go and see if it works. Okay, that's better. Okay, back to the PowerPoint. Oops. Okay, once again, it will be helpful if someone can just confirm that the presentation is working again.
Yeah, it's working now.
Okay, great, thanks. I'm just going to try and switch to presenter view in my end as well, then I can see my notes. And now I've gone to presenter view for me. Do you see all my notes and stuff at the side, or do you just see the presentation as you're supposed to?
Yeah, we just see the presentation.
Okay, great. Thank you. Thanks for confirming. Okay, so what are we working on today and in future? So I mentioned we've reached a really good point with the results to date. We've got like a really nice paper, and we're sort of we've really enjoyed demonstrating this thing can actually do something useful. But so now we know it's functional, we need to actually try and scale it up, because it's not going to be very useful if it's only a matrix size of 50 by 50. So just to sort of fill in the history of the project. In fact, I won't go through this in too much detail, but so I mentioned this has been going on for a few years. So we're kind of up to the Nature paper is where we are in the talk now, which is sort of mid to late 2025. But now the challenge is really scaling up. And actually, we've got a new exciting opportunity, which is coming from running large language models in data centers, and that's that the inference of large language models is itself becoming a very specialized process. And so, firstly, inference is very important in terms of the energy consumption. It's a really large percentage of the energy that's consumed in commercial deployments. So it's an important problem to tackle. And inference is split into LLM inference is split into 2 things. There's one thing called prefill and one thing called decode. And my understanding of this is not very good, but I think basically prefill is like you type in your prompt, and your prompt is loaded into some system, and the prompt together with all the context of the previous discussion you've been having with the system. And that gets you up to the point where you're ready to start generating tokens. And I think that part there is called the prefill. And that is compute bound, and it relies heavily on vector by matrix multiplication. And the second part is the decode, and that's where the system is actually spitting out the tokens. And that's not heavily reliant on that's actually heavily IO bound. So even if you sped up the computation or made it much more efficient, you wouldn't be saving much in that process. The graph on the bottom left there is supposed to show you that in the next generation of GPUs that NVIDIA are bringing out, they're bringing out specialized GPUs that are going to be the prefill and the decode GPUs are going to be different pieces of hardware. Amazon has a similar thing with their systems. So they have a thing called Trainium that does the prefill, and something called Cerebras that runs the decode. And so the exciting opportunity we've got is that we have a new, extremely important application, And also, we've started a collaboration with a startup who have a very fast metasurface technology. So now we have been relying up to date on spatial light modulators, which are 10 to 100 millisecond update times. And the problem with those is you can't change the model weights very frequently. So in all of the systems I showed you, the light propagating around the system at the speed of light, the model weights stay static for all of that time. And that basically translates into if you want to run an extremely large model on the hardware, you need to have a lot of weights on the hardware. But with a very fast metasurface, potentially as fast as a megahertz update rate, you can change that equation, and you can, with time multiplexing, effectively emulate a much larger number of model weights with still a sensible sized physical hardware. So as I mentioned earlier in the talk, we're still aiming for a 1 million weight module, optical module, but the ML model sizes we'll be able to emulate with that can be up to sort of hundreds of billions or trillions, which are the relevant parameter sizes for today's language models. So we've got this kind of two really cool things coming together. The first is a new application, which is really important and really important for sort of human scale energy consumption and electricity consumption, and potentially a new fast metasurface technology. So our current work is really involved in how are we going to scale this up and how are we going to make it work. When I say scale it up, I mean scale up the mathematical size of this thing so it can be a million sized. And going back to the picture that I showed you a few slides ago with the hardware, and I was highlighting when I showed that picture that the sources themselves are small, like tens of microns in size. The detectors can also be small, like tens or 100 microns in size. And the model weight, the spatial light modulator, that has 8 micron pixels. And so again, in a sort of centimeter scale thing, you can get a million weights, no problem. The thing that's big at the moment is the optics that couples all those two things together. So we are actively working on cleverer designs and different optical technologies to bring those optics down from sort of the 30 centimeter scale down to the hopefully centimeter scale, maybe millimeter. The other thing that really needs to change is that we've talked about how many pixels there are on the modulator, and today we've got enough pixels, but we're only doing 50 by 50 weights on a 1K by 1K modulator roughly. So we need to redesign the hardware, make it higher fidelity, the optics, so that we can use sort of one modulator pixel per weight. And that will involve adding very good calibration and alignment features. This is a picture of the team that's working today. So I'm James on the third on the top row, and Francesca's also on this call today. So hopefully a few of you will have questions afterwards. And Francesca is really leading the project, and she can hopefully give some answers to the questions that are too hard for me. And then that's the rest of the team. And then I also mentioned we've been doing some collaboration. So we've had collaboration with both internal Microsoft teams, and that was, for example, with the MRI work, and with external partners like Barclays. But with that brings me to the end of the talk. So thank you very much for your attention. Thank you for hosting me, and I'm happy to take any questions.
Thank you very much, James, for this very nice presentation. Really, we really appreciate a lot. So, any questions, comments to James? Okay, Benedict, I see that your hand is raised, so please.
Yeah, thank you. Thank you very much, James, for the very, very nice talk. I didn't have an idea of this topic before, so it's very interesting. I'm wondering about, let's say, could you speak a bit to the fundamental or theoretical limitations of AOC? So, for instance, when you say that the non-linearities, for instance, you implement electronically rather than optically, right? So I wonder what the ultimate reason for that is. Is there like a limitation precision-wise? Is there a limitation on the size of the optics? Maybe you can say a few words on this.
Are you asking particularly about the limitation for the nonlinearity there? Or
That is one example. But is there like could you scale this up to arbitrarily let's say have a ChatGPT that's running on AOC?
well, so firstly, if we can get this fast modulator working, then yes, the important point is there. Even though the system only has 1 million weights, you can and you will be able to run a ChatGPT sized model on the hardware. And we've got quite a lot of kind of computer scientists have been working on simulating that and working out just how fast would the modulator be to need to be. So maybe I should say a bit more about that and how that would work. So what you'd have there is you wouldn't have this closed loop feedback anymore. You would have your input vector, you would modulate that at gigahertz rates, let's say for the sake of argument, 10 gigahertz. And the matrix itself would be static for roughly a microsecond. So let's say it can update at megahertz, then it's sort of a microsecond on, a microsecond for switching, a microsecond on. So you would end up then with gigahertz modulated sources and then for 1 microsecond of time, your weights matrix is static. So you would then stream in a huge number of input vectors and collect a huge number of output vectors at the output while the weights matrix is static. And that would basically give you, so even though the hardware itself natively is implementing vector by matrix multiplication, you would have been able to do a matrix by matrix multiplication there, where the matrix is very rectangular. It's like in the numbers I gave you there, I think it would be 10,000 elements. The matrix size would be 10,000 by 1,000. So an input rectangle times 1,000 by 1,000, which is the sort of semi-static megahertz weights, and then an output matrix of 1,000 by 10,000. And then you would switch for a microsecond to a new set of weights, and then you would stream in another set of input vectors. And what you've done there is effectively you're able to, because it's happening on a microsecond timescale at a megahertz, you're able to chop up a much bigger input model with like really huge number of parameters and chop it into tiles and kind of step through those tiles and do the matrix multiplication in a tiled way, which is exactly what happens, by the way, on a GPU anyway, where the native tile size is like, I think like 64 by 64 often, and they're chopping up these huge matrices into 64 by 64 times things and sending them out to many systems in parallel. So that's the thing on like, could you run ChatGPT one day? I think the answer is like the simulations show yes. The nonlinearity and what's the limit there? I think Francesca's probably better at answering this than me, but I think basically optical nonlinearity at the moment is just an extremely high power, complicated thing. And I don't know if there's a fundamental reason for that, or it's just that there's not a strong enough nonlinearity that's been discovered yet that happens at low enough optical power.
Or let's say if it were possible to do it optically, what would be the advantage of overdoing it electronically as you're doing now?
I think you would be able to save on optical to electronic conversions if you were able to do optical nonlinearity as well.
Yeah, because they are noisy
and power hungry as well. Yeah.
Oh.
So actually, we've got a kind of a big model of the power breakdown in our system, and in this, it's a very different balance from a GPU. But in this system, a lot of the power consumption goes on converting from or like amplifying signals or converting from analog to digital. And so you want to do that as little as you can.
If it's okay with you, James, can I just, Benedict, also add, as you were saying, what are the limitations? Also, maybe thinking about bit precision. So obviously, what James has talked about, and we work in the team, is inference, not training. And this is very important because also the push today on inference is towards lower bit precision, because a big differentiator between digital and analog solutions is, in principle, we will have less precision. So the fact that already the industry is moving towards low bit precision for inference is a plus for us. So when we say we can run any ChatGPT, is with an asterisk of precision. That is one of the key issues that we have. Sorry, I just wanted to add in case this is where you were thinking of.
Yeah, yeah, exactly. Okay, interesting. Thank you. I have a few more questions, but I don't know if someone else has a question, they should go ahead.
I'm just checking actually. I don't see that, but I mean, as a follow-up, maybe. I mean, how do you see that? What would be the success of this look like for the AOC in few years' time? Because we already mentioned about the limitations, but what kind of success will happen by the AOC well, I don't know, in 2 years, 3 times, oh, let's say 5 years or 6 years. Could you please comment on that?
Yeah, I mean, so I think success looks like now. So having successful and working designs for a scaled up system that can really operate at like 1,000 by 1,000 scale, but also in parallel working on the understanding better the precision side of things, and like how firstly with machine learning models, what precision can you get away with? Like, can you go down to 6 or 4-bit precision and still get good answers? And on the hardware, can we get like really good precise vector by matrix multiplication results at the required precision for machine? So it's like as a research problem, there's still a lot to tackle. It's not so. This is not like a sort of a tick box for the research, and we're trying to suddenly make a product here. There's lots of kind of hard research to do.
But if we are successful, just to complete what James is saying, in 5 years' time, what we could have is an optical coprocessor that could be 50x more energy efficient as compared to baseline GPUs. So the dream is to have an optical coprocessor that is much more efficient than what digital hardware is today.
Okay, thank you. So I think you can go ahead, Benedict, because I don't see any hand raised in the
Yeah,
meeting.
I was just a few more little questions. So for instance, to build your digital twin that you use for as far as I understand, you're doing the forward pass in the actual system, but the backward pass in the digital twin to back propagate. Is that right?
So during training, the forward
Yeah.
and the backward
Yeah.
passes are done. During training, the forward and the backward are done digitally.
Forward and backward. Okay.
And then
Okay.
it's inference where the forward pass is done.
Would it make sense to do the forward pass on the actual system? No. Okay. Francesca is shaking their head. Yeah, right.
Yeah.
Okay, but
yeah.
For the digital twin, which tools are you using? Are those open source?
It's a big Python model. Yeah.
Big Python model. Okay.
And actually, if you're interested, I believe in the Nature paper that we submitted, we have some code, right, James?
Yes. Yes, I think it may be all there. Yeah. Yeah.
And just for clarity, training is not convenient because what you do in training, you keep changing the weights. And this is something that is not the strength of our hardware. We want to have the weight as static as possible to gain the energies that we require. This is why we focus on inference rather than the training side.
Okay, I understand. Okay, and that almost leads to my other question. Would you be interested in or are you interested in other use cases, for instance, from particle physics? I don't know if there are, if we can provide examples for you or applications or use cases that would be of interest for you. If so, you can think about it, and of course you can reach out.
I think we're always happy to discuss. And yeah, it's for the applications so far, it's not been a case of just take an existing application and dump it onto the machine. There's been quite a lot of collaboration between hardware design, and so it may be that it's lucky and something could work, but I think the expectation would be that it's not just a sort of it's not just like a general purpose machine learning thing that you can dump a problem
Yes.
onto and it'll work.
Yeah. Okay. And my final question is, well, is it probably the answer is no, but is there like a natural segue of AUC into photonic quantum computing, like basically working with individual photons rather than what you're doing?
Okay. Have you got a good answer for this, Francesca? I'm thinking at the top of my head.
They are very complementary to quantum. So in my dream, at least, there is a quantum computer, there will be an AOC coprocessor and GPUs. And depending on the specific applications, you go for one versus the other. So maybe this is the shortest answer to your question, if it makes sense.
But it would probably be an entirely different system then, right? Yeah. Okay. Yeah, thank you. Those were my questions. Very interesting.
Okay, well, yeah, thanks very much for having us.
Thank you very much, Benedict. So any other comments or questions? So I don't see any hand raised, and people are just thanking to you, James and Francesca. I really would like to thank on behalf of our cost action. Thanks for reserving some time for us, and it was a great pleasure for us to welcome you in our first Colloquium series. So I think we are done, and then I still don't see any last minute questions. So thank you very much. So I think we can